Hi, so I'm going to talk a little bit about like the basic data computations that we do with a data set in this class. So here we have a list of data, just a bunch of points, independent of some context. So there's a bunch of values between 1 and 7. We throw them into this list here, and what we see on the right here is a graph of each of the, let's move this aside here so we can zoom in a bit. Each of the different values in our data set and its frequencies. So there's 1, 1, 2, 4s, 6, 3s, and so on. Now, in general, when we have a bunch of data and we want to um, construct a useful summary of that data, there's typically two things that are measured. One is a uh, measure of centrality, so some sort of value that tells you where the middle or center of this data is, and some sort of measure of spread or variance or how wide the data is. So, and the reason we have those two things is because um, we typically speaking, when we collect data from a larger pool of data, like let's say you're trying to find the average weight of a group of people or the average height, um, you typically don't get to interact with every single member of the population that you're working with, right? And that's much of what the first half of chapter one is about. Typically speaking, you only get to interact with a handful of data points, whether it's in the dozens or the thousands or tens of thousands. It's very rarely the entire population. And so, what you want then is you want to be able to do two things. You want to be able to make predictions about what the population does, and you also want to be able to have some sort of gauge on how good that prediction is, like whether or not we can be, safe and comfortable with that prediction, or whether or not that prediction is, just a shot in the dark, so to speak. And so you want to know two things. You want to know what on average is happening with your data, and whether or not that something is something that that your data points tends towards, or whether or not they're all over the place. Uh, you want to know basically if your data is really spread out or if it's really concentrated, so that your notion of centrality, how well does it represent that data set, basically. And so one way of measuring centrality and spread is with the mean and the standard deviation. Now, the mean is the typical mean we've probably seen before in other courses. And so what we'd have here is we have it's calculated by taking all these data points, summing them, and dividing it by, in this case, 18, right? Data points. And so here we have that computed automatically. We get a mean of 3.4444, etc. repeating, and we can see it plotted here, right? And it does seem like it's right in the center uh, of our data. And so we have two notions of standard deviations: the population standard deviation, the sample standard deviation. Um, so the population standard deviation is what we get by taking all of the data points, taking their difference from the mean. So in this case, I would take 1 and 3.444, taking that difference, squaring it, adding them all up, dividing that by 18, and that gives me what's called the variance of the spread of data, and the square root of that variance is the standard deviation. Now, sort of why that is the right notion of variance, or right way to measure spread, is a little technical. I do have a handout in D2L, which sort of goes into that into a little bit more detail and walks you through a thought experiment. But uh, for now, we'll just say that if you were to take, let's say, if you just were to have two data points, let's say 1 and a 2, right? The population standard deviation, the variance, and the standard deviation we see here, the way we would formally compute that is, well, for the variance, what you would take is your first data point, its difference from the mean squared, and to that we would add the second data point from the mean squared, and that gives you your variance, which is sorry, and then this whole thing over 2, and that's your variance, right, which is what we see here. And then your standard deviation is just the square root of this, which is 1/2, which is the standard deviation we find here. And if we just look at this formula, it's maybe a bit of a stretch, but it's very reminiscent, isn't it, of the distance formula? Like if you have 2 points x1, y1, and x2, y2, the difference from x1 and y1 from x to y2 is computed by something like the differences between them squared, taking the square root. Now we're dividing by the size of the data set here to kind of offset for the size of our sample, but that's really how we want to think of the standard deviation. It's like sort of a distance from any given data set from its mean. And so the wider, the less like its own mean it is, the wider the standard deviation. So we can take two data sets with the same mean, let's say 1, 1, 1, 2, 3, 3, 3. That's definitely going to have a mean of 2, and its standard deviation is about 0.925. And a different data set with the same mean, let's say 0, 0, 0, 4, 4, 4 is also going to have the same mean, but now everything's farther away from the standard deviation, so we get larger values for that. All right, great. And so the population standard deviation measures for a population, for a set of data that represents the entire population, the sort of variation or the sort of distance from the mean of that data set. The sample standard deviation is computed slightly differently. We just take the denominators and subtract 1 from those. So let's go back to maybe our basic example here, 1, 2, and a variance of 1/2, and then the square root is 0.707 something, which is our variance and standard deviation here. The sample standard deviations are computed by the exact same way, except we decrease the denominator here by 1. And the reason for that is somewhat technical. It's so that the sample standard deviation is an actual good predictor of the population standard deviation. Uh, an important thing to remember then is that if you can access the entire population at once, then you can uh, use the population standard deviation. Otherwise, we use the sample standard deviation. And the important thing to note is that the sample standard deviation really is the standard deviation that matters, because if you can access the entire population of something at once, you wouldn't need statistics. You would have literally all the information in front of you, and there's no reason to do any extra work to try to predict anything. So uh, the sample standard deviation is the one that's really cogent here. It's also worth noting that if you only have one data point in your data set, and then the sample standard deviation is not defined. And that should make sense because, first of all, if you have a data set, if you took a sample with only one data point in it, how are you supposed to measure how spread out the data is? You only have one point, so how are you supposed to know that? And second of all, you really shouldn't be doing any statistics if you've only taken literally one sample. That's that's sort of an absurd thing to even uh, try to think about. But to kind of get a sense of what's happening with the population sample standard deviations, let's go ahead and throw in a bunch more numbers. Let's say 3, 4, 5, 3, 6, 5, 1, 2, 1, 4, 3, 2. Okay, so there we go. We have a bunch of data points of our mean here, just above 3. And so what we imagine with the sample standard deviation is that it's sort of a width within which a bunch of our data falls. And so what you'll hear us talk about later on in the class is, how many standard deviations something is away from the mean, and that all that refers to is, is it, pretty close to the mean? Is it, far away from the mean? Is it really far away from the mean? Is it a real outlier event or a kind of central event? That's what the standard deviation will measure in those cases. All right, so mean and standard deviations is one way of measuring centrality, and it's usually the primary way of measuring centrality. Another way of measuring centrality is with the 5-number summary. So this measures both, centrality and spread. And so the 5-number summary is, given a set of data like we have above, the smallest data point in that set, the median, which most of us remember as being the middlemost point of the data set, the first quartile, which is so the median divides, so the median, sorry, I'm pointing and no one can see my finger. The median here divides the data set in half. So that means half the values are above 3, half the values are below this 3. And so what the quartiles do, here we have the lower quartile, or Q1, the upper quartile, Q3, is between the median and the two quartiles, we divide our data set into 4 pieces. The lower quartile, the next quartile, the next quartile after that, and then the last quartile. And so Q1 and Q3 really represent the median of the first half of the data and the median of the second half of the data. So if the first median cuts your data in half, then each of the other quartiles cut their respective pieces in half. And so if let's move this smaller so we can see it better here. What we have here, if I click my 5-number summary, is a box plot, right? Where, okay, 1/4 of my data is here, 1/4 is here, 1/4 is here, and 1/4 is here. And so this is another way of measuring centrality. And then our center here would be median 3, and the corresponding concept rather than standard deviation is IQR, which is the difference between the first and third quartiles. So this length here between 2 and 4.5 is the IQR, and so that would be 2.5. And so when I was a stat student, when I first learned this stuff, uh, my kind of natural instinct is, why do we have two different competing notions for uh, centrality and variance, right? Like, why do we have mean and standard deviation on one hand and five number sum on the other hand? What's the point of having two different concepts? And so I'm gonna go ahead and sort of illustrate that with a little thought experiment, like why we would need two concepts. Let's say you go to a party and you walk around and you uh, poll people as to how many drinks they've had so far. So you ask the first person, it's 0, and then 2, and then 1, and then 0 again, 3, 2, 2, 1, 0, 4, 2, 5, 1, 2, and then the last person you talk to, let's say, is 25. All right, and so if we go ahead and look at what our kind of histogram looks like, we get most of our clustering of data here, and then this data point here. And so we have our mean here of 3.3333. And if we were, this is a sample, this is a subset of the people in our party. If we were to take a look at what our standard deviation is like, it's relatively huge. Our mean is 3 and our standard deviation is 6 something. And if I were to plot that, that's like almost everyone. In fact, everyone falls within one standard deviation except for this data point here. And so there's two thoughts here, and that is, one, that doesn't really seem like a good mean, right? After all, if I ignore this data point here, out here, this isn't really in the center of my data, right? Most of my data is over here, and it's only because of this 25 that my mean's so high. And it's also only because of my 25 that, oops, sorry, I want that my standard deviation is so wide, right? Like, otherwise, it doesn't seem like it should be this wide. My standard deviation seems like it should just be like a couple of points, maybe, right? And we can confirm this by going back up and being like, all right, what happens if I get rid of my 25? And then, yeah, without the 25, my standard deviation drops down to 1.4 something, and my mean drops from 3.3 something down to about 1.8. Like, that's a big drop, right? So this one data point in our data set really screws up our mean and standard deviation. On the other hand, if instead of looking at the standard deviation, I look at my 5-number summary, all right, here's my Q1 is 1, Q2 and Q3, my median and Q3 are both 2 in this case. If I throw in my 25, okay, that bumps my Q3 up to 3. That's not really a very big difference, right? And my median is still 2. So let's take a look again. Without my 25, with my 25, without my 25, with my 25. And so, oops, sorry, with my 25. All right, so what do we notice here is that, my median doesn't change at all when I throw in this extra huge data point. And my IQR doesn't change very much either. It goes from 1 without the 25 to 2 with the 25. And so that's a very much smaller change compared to uh, the change in my standard deviation, for example, which went from uh, trying to remind myself what it was even, right? 6 something 1.47 something, right? And so one our preferred method for um, centrality and variation is the mean and the standard deviation. There are theoretical reasons for why those concepts are valuable, but it's important to keep the 5 number summary and have median and IQR in our back pocket because um, as a measure, it's much more robust. Uh, and it handles the presence of outliers and throwing in weird sort of uh, out there values much better. Another reason to have both the mean and the median is for comparison purposes. So let's say we don't have that 25. Then my mean and my, let's kind of get rid of that here. Then this is my distribution of data. My mean is 1.78 something. And then if I look at my median, it's a 2. So plot that in, it's right there. They're pretty close to each other, right? And if I look at the actual curve, the shape of my graph, it's not exactly symmetric, but it's not super skewed, right? Uh, so if I look at this, I say, okay, yeah, there doesn't seem like there's a lot of skew to my data here. On the other hand, if I go ahead and throw in, no, I don't want to save that. Let me just open. All right, so I accidentally deleted that, which isn't great, but I can just reload this. So let me just go ahead and throw my 25 in here. Or let's use this as a new example. So this is just a bunch of data points. So there's my mean. And the median for this data is a 3. So same deal, right? There's if I plot that, my mean and median are pretty close. The graph's more or less symmetric. No real lean or skew to it. So let me throw 25 in here. So there's that there. And now all of a sudden my mean is way bigger than my median, right? And like I said, it's because the mean is sensitive to a large data point like this, right? This 25 adds in a big number to the sum of the total data, which when divided by the total number makes a big difference. Whereas for the median, the median only cares about what the centermost values is. It doesn't measure or doesn't care about what's on the outside or on the fringes. So throwing in this 25 doesn't make a big difference. So in this case, our mean changes a lot. Our median doesn't. So we can say, oh, there are data points skewing this data to the right. And so there's a possible right skew to be detected when the mean is so much greater than the median. And you might guess if I throw a negative in front of that, and so I pull it out here, now my, now my mean is much smaller than my median. It drops down a lot, and again, it's because the mean is much more sensitive to this negative 25. The median really doesn't care, so the median's still 3. The mean drops down. So since the mean's much less than the median, there's possible left skew, right? There's this left data point shifting the data to the left. All right, so hopefully that answers some of the questions that people have been asking about this assignment. I'll be talking about probability here pretty soon. Please stay tuned, and thank you.